discuss how to measure phase and frequency. I hope we probably managed to do it today, and or if not, we actually continue the next classes already after the holidays. Well, so the first concerning the electromechanical panel meter, despite the generally measurement nowadays are the digital processing, we still have sometimes some advantage of the electromechanical meters, and one of the one of the advantages of the there is actually several advantages of the electromechanical meters. First of all, its price, they are ready to operate. They use actually the scale, and they are very well when we are going to look at the change of some not so fast changing signal. So actually just observing how the index oscillating or how the index moving, we may make some prognosis and percept the value in a more convenient way. Of course, for the accurate measurement, when we're going to fix and to put on a paper or to put in a memory some numbers, it's not so convenient. But for the, let's say, for the runtime monitoring of the process, electromechanical panel meters still are quite fine. Well, so the principle of the such kind of operation is usually some kind of magnetic or electric force that provide a turning momentum, rotational momentum to the index, and usually the frame of the index is attached, has a spring or torsion spring, either some helical spring attached to it, which provide actually some return moment, and the moment that force the index to turn usually depend on the current or on the voltage applied to the device, and from the other hand, the moment of the returning force from the spring usually is proportional to the deflection angle. Due to this, we actually have an equilibrium when the moment of the current moment caused by electric current is compensating by the moment which is related to the spring. So we have some kind of balance of equilibrium at for every value of the current flowing in, and that's why we actually have some kind of relationship between the deflection angle and the current. In other words, the deflection angle is actually the function of the current flowing through the device. Generally, as you see, most of the electromechanical panel meters are, let's say, born as a ammeter, so they react on the current. There is one exception, the voltmeters, which are actually the device, also called electromechanical, one of the electrostatical devices, which are intrinsic voltmeters, so they react on voltage. So, and anyway, if we consider the sensitivity of electromechanical panel, we could describe the sensitivity as having a three component. So the first one of all, it's a relationship between the mechanical momentum, which is which causes the index frame rotation. So it's dependence of this mechanical momentum on the current. So this is the first component of sensitivity. So how big the momentum is providing certain current. What is the change of momentum? The next is what is the change in the rotation angle of the index or deflection angle of the index, providing we have certain momentum. So the sensitivity of the angle to a mechanical momentum, and then the sensitivity of the actually number of ticks on a scale in respect to the rotation angle. So what is how many actually ticks, scale ticks or tick marks, yeah, we have when the index deflects by certain angle. So, and finally sensitivity may be expressed as the tick units per current for instance, or per voltage. So, for instance, so many ticks per volt, or so many. Generally, when the panel meter is not dedicated to measure certain value, it's usually just have the ticks, which corresponds, or the all span of the ticks corresponds to the measurement range, to the input range of the meter, but generally they may even not be marked as this as volts. And as a designers, as the engineer designers, which make some project, we often may just change the scale and make the scale correspond to our needs. So we may actually replot the scale and use and mark here whatever units we need. Finally, in any way, we have some. We could understand that we actually have some deflection angle if we put this electromechanical panel meter as the final stage in our measurement chain. So we could understand that we actually have a deflection angle as a reaction on the input value, and we actually have to design how to plot a scale, bearing in mind the sensitivity of all our measurement chain. Okay, up to the mechanisms itself. So one of the most used now, still in a great use, is a magnetoelectric mechanism, which consists of the moving coil with an attached index and a spring, which provide a return momentum, keeping the index at zero value without when the current is not applied to the coil. And the moving coil is placed in a magnetic field provided by the permanent magnet. So the magnets may be different. So sometimes magnets is like a core type magnets inside the coil. Sometimes there is a disc or ring magnets around the coil. Usually it's a ring magnet around the coil. And this ring magnet, which is placed around the coil, it plays a two role. From one hand, it's provide a magnetic field. From other hand, it's provide a screening or shielding of the coil from some external magnetic field, because it's a conductor. So usually, so here we have an index. Sometimes the counterweight is added to the index to help him to rotate for the cheapest device, but usually there is some counterweight. So here is a two helical spring, and actually that is all design. So for the small mechanisms, so very seldom such a big a Horseshoe-shaped magnet is used. Usually it's a cylindric type magnet. It's just around the coil. The relationship between the angle, the deflection angle, and the current flowing through is here is a linear, and the coefficient is defined by the magnetic field by the magnetic field strength inside the coil. So this magnetic induction value, the number of the cross section of the coil, the area of the coil, and the number of the turns in a coil, and is the W. It's a stiffness of the angular, actually stiffness of the helical springs. So this hereby the deflection angle is proportional to the current, because the field is a constant. Yeah, the deflection is proportional to the current. The magnetic mechanism very often are marked with such a signs, which is depicted on the scale of the device. Sometimes they may be marked, sometimes no. Magnetoelectric mechanism is intrinsic DC mechanism. It couldn't work with AC. It's absolutely clear. So because if it works with the AC, when the current changes direction, the momentum which turns the index turns the direction too. So the index tends to oscillate. So if we have a very low frequency current, then we have DC currents, AC currents. So we have the index just moving back and forth. If we have a high frequency current, So the inertia of the index doesn't allow it to move fast. It just actually vibrate near the zero or doesn't deflect at all. So magnetoelectric mechanism could be used to measure a DC current. In DC current, we have to convert the AC to DC before using magnetoelectric mechanism. But from all the mechanisms, magnetoelectric are the most sensitive. Generally, they may be extremely sensitive because we may select a magnet with an extremely high, very high magnetic field. We may make the coil very weighted with a low inertia moment, and we may take quite a low stiffness springs. And sometimes we see the magnetoelectric mechanism is used in so-called photogalvanometric measurements when we actually doesn't use an index at all, and we use just a beam, light beam, which reflects from a tiny mirror attached to the axis of the system. So in this case, the inertia of the system is very small, will be quite small as it's possible to be for the mechanical system, and the sensitivity will be very high because the deflection angle will be very small. Such kind of high sensitivity devices, high sensitivity galvanometer may be so sensitive that they react even all the thermal fluctuation of the air pressure around the coil. And the thermal noise actually become a problem in a minute. So the other examples of the electromechanical mechanism is electromagnetic mechanism. Here we have a non-moving coil. The current is passing through the coil. A magnetic field which appears magnetize the core, some movable core, and the index is attached to the core. So when we add a current, we put a current into the coil, so then the magnetic field actually magnetizes the core. The core will be pulled inside the core, inside the magnet. It's actually like an electromagnet works. And the core piece of metal, magnetic metal that actually are attracted inside the coil. And as the magnetic field is in the coil is proportional to the current, and the magnetization of the core is proportional to the magnetic field, and it means it's proportional to the current too, the deflection angle totally is proportional to the square of the current. So the electromagnetic mechanism is not linear. It could be linearized more or less to the nonlinearity by selecting a special shape of the core, and the shape of the core may be quite a complex, and this shape of the core may actually alter the momentum which appears when the core go inside the magnet, and this actually the relationship between the forces or the momentum or the which appears when the magnet starts to work, and the deflection angle may be quite complicated and expressed here as this derivation of dL by dA, where L it's a mutual inductance, mutual not inductance, it's mutual induction coefficient between the coil and a magnet core. So by changing a tricky shape of the core, it's possible to reduce a little bit nonlinearity, but generally the device is nonlinear. As it's nonlinear, as the deflection angle is proportional to the square of the current, electromagnetic mechanism may be used for the AC measurement. Because whatever direction the current have, the force between the core and the magnet always is an attractive force. Because the magnet, independent of the direction of the current, the direction of the magnetic field will be changed, of course, in the one direction. But magnetization which appears in a core always will be related to this external field, and always will be in this direction that the core will be attracted to the electromagnet. Another feature of the electromagnetic is they usually have to have a damper. So we need to add a damper. Here is an example of how the damper looks like. In this case, it's a curved box with such kind of flag moving back and forth. The role of the damper to provide a viscous friction to stop the oscillation of the index after the device is switched on. Another feature of the magnetoelectric mechanism doesn't require such a damper, because if the coil starts to oscillate, the magnetic induction from the constant field of the magnet induce a current inside the coil, and the current is directed in such a way that prevent actually the movement of the coil. So magnetoelectric mechanism is self-damping because of the electromagnetic induction. And one of the methods how to check whether magnetoelectric device is operational or not, you have to shortcut its output, actually the shortcut of the coil, and try to rotate it a little bit, making an index to move. If you see that index is the oscillation of the index when you shake the device very fast, fade very fast, so your device is okay. If so it means that the coil is intact. If it's oscillate readily, and it doesn't fade very fast, so it means that your device is broken, and in fact the coil is burned out. So there's some more contact inside the coil, because this electromagnetic induction doesn't work here. For electromagnetic mechanism, we need to add a damper. Another example, some variant of the electromagnetic mechanism is so-called electrodynamic mechanism. We have two coils here. There is no some magnetic material, but just two coils. One coil is a stationary, and another coil is movable. So if we write down every coil produces some magnetic momentum with the current flow through it, and then these magnetic momentums are interacting, providing a mechanical. So if we write down try to express how the deflection angle depends on the current that flows through the first and second coil, we find such an equation. So it's nonlinear too. The deflection is actually proportional to the product of these two currents. Generally, yes, and this dm by d alpha, the m here is a mutual induction coefficient. Yeah, I'm sorry, here the L, it's the inductivity of the coil with an inserted core. So then if the core have a very uneven shape, so then the change of the inductivity with the change of the angle here, when the rotation angle increase and the core go inside the coil. Yeah, so the dependence of inductivity on angle may be nonlinear too, to compensate nonlinearity. Here generally it's no way to compensate, because it couldn't change it usually doesn't change the shape of coil. So that we actually understand that this mechanism is not linear. So the electrodynamic mechanism may be used to measure a DC and AC current too, if you pass the current through the first coil and immediately through the second coil. So then the deflection angle is proportional to the square of the current. But electrodynamic mechanism may be used also to measure some other value, for instance the power. So if we have if we provide one current dependent on the applied voltage to pass a current that is proportional to the applied voltage, and the second current will be just a current that goes into the circuit, and the product of the current which is proportional to voltage and the current that is just go through all our loads, through our network. So this product will be just proportional to the power of the current. And this way we may use it as a measure to measure the power. It's making measures really the product between two currents too, but it's generally nonlinear. And finally, an electrostatic mechanism, as an example of the last example of electromechanical mechanisms. So the static mechanism operates very simply. It's quite close to the electrometer you probably have seen in your school, when a teacher actually charge the plastic rod and attach it to some device which has an arrow that deflects as the device become loaded. And here is a similar principle that we actually have two electrodes, a stationary electrode and rotational electrode, and when we apply a difference in voltage difference between the stationary electrode and rotating electrode, so they got an electric force between them, and the rotating electrodes try to be pulled inside the stationary electrode, providing hereby the deflection of the index. So we have to have here the spring 2 and the damper. So, and electrodynamic mechanism usually has a damper too. Comparing to all other mechanisms, electrostatic is one of the less sensitive. So it's actually start to work from the voltage is more than 10 volts. And even more than 50 volts. But it may be used to measure the AC voltage too, because the deflection of the index is proportional to the voltage square of the voltage. Well, so this is concerning the mechanical devices, but any mechanical device actually should be, when we try to calculate how the circuit, which includes the device, we should take into account the equivalent circuits of the device. Usually when but it's actually it's a case for any device, not necessary. It's not necessary to speak about the mechanical devices. For the electronic device, we have the same issue. So when we discuss some device which have to work with the ammeter to measure current, we have to take into account that the device has its own resistance. For the ammeter, so then we represent the ammeter as the ideal ammeter, which doesn't distort current inside in the circuit and has a zero resistance and effective resistance of the ammeter. So of course, for the ammeter, we are interested that this resistance should be as low as possible. The lower there is resistance, the less the ammeter distorts the current in the circuit it's inserted. The voltmeter, the device which measures voltage, is replaced by such an equivalent circuit when we understand that we have some voltmeters resistance, effective voltmeter resistance, and we have the ideal voltmeter with the infinite resistance. So for the voltmeter, we are interested the resistance will be as high as possible. So if the resistance is very low, we got that the voltmeter actually shortcuts the element or this part of the circuit when we measure voltage. So this is two equivalent circuits, ammeter and a voltmeter. Our dream is the zero resistance for the voltmeter, for the ammeter, and infinite resistance for the voltmeter. Some parameter for to have some perception what the magnetoelectric ammeter may provide. Generally, so the budget class ammeters provide a current measurement in the range from 0 to 100 milliamps, but actually is quite enough. From 0 to 100 milliamps. As we see, we may use these ammeters to work with the higher currents as well. The typical square interval for such a magnetoelectric ammeters is from 1 to 2 milliamperes per one scale range, actually distance between two ticks. And usually the accuracy of such a budget class magnetoelectric meters is from 0.5 up to 5. No, for 5 it's quite big. Yeah, 5 it's 5% of the range. For 10 milliamps, the accuracy is about 5 milliamps plus minus, so it's not so accurate device. But for the accuracy class 0.5, it's fine. So we will have the for the 10 milliamp, 100 milliamp device, we have some uncertainty of measurement of around 0.5 milliamps. That's quite good. Very seldom the ammeters is manufactured with a smaller current, but I have seen about up to 20 milliamps, 50 milliamps. Very seldom it's lower. If you need a lower currents in the microampere or nanoampere range, we usually use an electronic ammeters. To compare the accuracy of magnetoelectric ammeter as a final stage of your measurement device, let's compare it with an analog to digital converter, which actually, for the typical converter, which has a 10-bit and could digitize the input into about 1,000 values. For the input range from 0 to 3 volts, the digitizing error will be about 3 millivolts. So they are more or less compatible. Actually, if you have 100 values and the digitization error is 1 per 1,000, so it's about 0.1%. So, but in any way, whatever device we would use, either it's magnetoelectric ammeter or it's an analog to digital converter, we need to adjust the measurement signal to be compatible with one of the corresponding device. So for magnetoelectric amp, we have to provide that the currents flow at the end of the instrument will be in a range from 0 to 100 milliamp. For analog to digital converter, we need to adjust it to the range from 0 to 3 volts or to 0 to 5 volts. So we have to design our measurement instrument in such a way that the input of the final stage will be input signal which comes to the final stage, which corresponds to the input range of this final stage. For this, we often may use the transducers. And there is two types of simple transducer. They call it a shunt resistor and additional resistor. Usually just use the word shunt. These simple transducers are this looks like just a resistor. Allow us to, first of all, to expand the range of the instrument. We couldn't compress range. We just couldn't go from wider range to the narrower, but we could go from the narrow range to the wider. So we could use it to increase the range of the measurement instrument, and we use it to convert current meter into voltage meter and vice versa. So actually here we have two important functions to convert current to voltage, voltage to current, and to adjust the range. Let's see, for instance, an example of using of the shunt resistor. So we name as a shunt resistor. It's a resistor that actually that allow to bypass the device. It goes in parallel to device. So if I have an ammeter here, and the shunt resistor provides some kind of bypass. It doesn't provide 100% bypass because some part of the current still will be directed through the amp. But the ratio between the current going through the shunt or through the bypass way and the current proportion that goes through the ammeter, these two could be very different. So if you try to consider the operation of shunt resistor together with the amp, so what we actually what we will get, yeah. Let's consider this circuit. So first of all, what we could say that the current that flow into this total system ammeter together with is just a sum of the shunt and the shunt current and the ammeter current. From another point of view, we may say that the voltage over the shunt is equal to the current flowing through the shunt and the resistance of the shunt. And this voltage will be equal to the voltage over the ammeter. So the current through the ammeter is equal, the voltage over the ammeter will be equal to the voltage over the shunt because of the parallel connection, but the current flowing, but the voltage on the ammeter, from other hand, may be described as the current through the ammeter times resistance of the ammeter. So joining these two equations together, this one, the E shunt, R shunt is equal to I ammeter, R ammeter, and this one, the current flowing through all the system is equal to the shunt current plus ammeter current. I get a relationship between the current through the ammeter and the total current. So the total current will be equal to the current of the ammeter times this kind of multiplier, 1 plus RA divided by R shunt. So I use this letter shunt for the, yes, it's a Latvian letter for sound sh. Okay, let's mark it like this. So actually, what happens? So if the shunt resistance, this resistance, it's much more less, it's less than ammeter resistance. So then I have the current flow through both these channels will be higher than current that flow only through the ammeter. One way it always will be higher, but if I take, for instance, RA 9 times higher than the, if I take the shunt resistance 9 times lower than the ammeter resistance, I will get that the current that flow to the will be 10 times higher than the current to the ammeter. So by this, I may to extend the range of my ammeter. So adding a corresponding shunt. So if I have, for instance, an ammeter, which could measure only up to 100 milliamps. So if I add a shunt, which is 9 times less than the ammeter resistance, I will get the totally that my ammeter now could measure currents up to 1 ampere or 10 times 100 milliamps. So and of course, I should make a recalculation, but my own. I understand that the amp show me a 10 times lower current, but by multiplying it by 10, I may reconstruct what will be total current to all the system. This ratio may be very high, in fact. So we may take a ratio of around up to 10 in order of 3. So with the 10, we may measure the currents which are actually much more higher than ammeter currents. So this is a way how to extend the current range of the ammeter. Here is an example how we use shunt to transfer or to actually transfer the voltmeter meter into ammeter. So this here we use the shunt. We put the shunt in a circuit, and the current flowing through the shunt by the voltmeter measure the voltage over the shunt. So, and this, of course, we understand that the part of the current doesn't go through the shunt. The part of the current still goes through the voltmeter. And one more, so we consider one more the sum of the total current of the total, how the total current is made of or divided into the shunt current and the voltmeter current. So then following the first Kirchhoff law, this equation should stand, yeah. And then we actually understanding that the voltmeter and the shunt is switched on a parallel, is connected in parallel. So we just go there, get the relationship between the voltage, what we do see actually, and the shunt current. So and the total current. So grouping one more these equations together, we will get the relationship between the current which is flowing through the shunt and through all the system together, and the voltage what the voltmeter is measuring. Here we often consider that the voltmeter has a very high resistance comparing with the shunt. Generally, we are interested to have shunt resistance as low as possible, not to disturb the current through the circuit, so to provide as less resistance the current that flows here. So then very often we just ignore the voltage, the resistance of the voltmeter, and look only on the resistance of the shunt, which is actually less, much less than the resistance of the voltmeter. So this term will be much more higher than this term. And we got actually absolutely obvious relationship between the measured voltage and current that is flowing through the shunt. Like from the Ohm law, that the current is just voltage divided by the shunt resistance. If our measurement doesn't require too high accuracy, we may actually ignore this RV. If you need a very high accuracy, we actually have to take into account this RV. And then we're calculating the shunt, so we have to take into account with what voltmeter will our shunt operate, and we generally find the shunt to have this coefficient between current and voltage to be very convenient. For instance, proportional to 10 or something, some kind of 10 or 100 and so on. Yeah. This circuit, please note this circuit. So this circuit is actually a standard solution how to measure current device which actually measure voltage. So as we see in our previous lectures, we mostly discussed different kind of voltage amplifier. For instance, the instrumental amplifier actually amplify voltage. Why voltage? Because the analog digital converters mainly are operating on voltage. So they are convert voltage. So we need voltage to make a measurement to convert the signal into the digital form. And if we need to measure current somewhere, so for the digital device, usual way will be to have a shunt, to have it flowing through the shunt and have some kind of voltage measurement device. It may be, for instance, an instrumental amp. It may be already a digital to analog converter if the current is high enough to cause a voltage enough for the analog to digital converter. But anyway, we use this shunt resistor to convert current into the voltage. Another example, when we use, so both of them, they are named shunt because it's connected in parallel. If the resistor is connected in series, it's called additional resistor. If we connect the additional resistor in series voltmeter, which has a high resistance by itself, so we understand that the current which is flowing through is the same, but the voltage, what we apply to the end of the whole assembly from this point to this point is actually sum of the voltage which fall over the additional resistor and the voltage that fall over the voltmeter resistor. Actually, one more, we have these two equations. So the sum of the voltage is equal to the total voltage and the current separately flowing through the one resistor, or the additional resistor, or to the through the voltmeter. They are both equals because they are current flowing through series connection. From these two equations, we got the relationship between the voltage measured by voltmeter and voltage applied to the whole series. And we see in a similar way as we have it with the current in shunt resistor, here with additional resistor, we can get the higher voltage over the whole series comparing to the voltage applied to the voltmeter itself. So we could extend the voltage range of our system. So the resistor RP may be so high that the voltage indeed may be very big. So typical examples, I have the typical voltmeter is measure up to, for instance, 100 volts. So we apply several kilo ohm or even mega ohm resistor, additional resistor. We may measure the voltage up to kilo ohms. Of course, here will be some problems, purely technical problem to prevent this resistor from breakthrough. But nevertheless, so it could be done. So we could measure very high voltages. And here is example when we add the resistor, additional resistor, the microampere meter, the milliampere meter, and make actually the voltmeter. So the voltage over the whole assembly is the voltage over the additional resistor, voltage over the ammeter, and the voltages, every voltage could be related with the current that flow through the whole assembly. And we may relate the voltage, which is attached to the, applied to the whole series, to the current which is flowing through the ampermeter. So here actually, no, and this actually is a transformation of the milliamp of the ampermeter into voltage. So this additional resistor allows us to use an ampermeter voltage. Here is not so important what is the relationship between RP and RR. If we actually usually use P high enough, so we may neglect RR and be happier. So this one more, two simple transducers, additional resistor and a shunt. So some additional circuit which is used in a simple measurement device using an additional electromotive force source, or say additional voltage source like a battery. If it's a power device which is powered with some kind of AC circuit, so it may be just some voltage source, but for the handheld device usually it's a battery or a accumulator or some or other additional electromotive force source. In the modern devices, usually the battery feeds the electric stabilizer, which provide a fixed voltage independently of how the battery is reloaded. It's not reloaded, that's actually how battery is depleted. So while the battery voltage is still over this stabilizer voltage, the stabilizer will be provided fine good voltage, fine stable voltage. So when the battery usually drops, voltage drops below the stabilizer voltage, so usually there's some kind of indication show that your battery is totally depleted, you have to replace it. So, well, but anyway, so when we have such a source or electric force, we may use it additionally to measure resistance. And actually there is two types of how to measure the resistance. And first example is when we attach some additional resistor R0 in a series with a measured resistance. We put a current through and we measure the voltage which is drops over the measured resistor. So if we calculate what will be the voltage, what the voltmeter measure, neglecting actually the internal resistance of the voltmeter, considering it's nearly infinite. So we easily find that the voltage over the resistor Rx will be actually the electromotive force divided by the voltage of divided by the total resistance of this loop circuit, R0 and Rx, and multiplied by Rx. So if R0 is much more higher than Rx, so we ignore the Rx, and then this equation transforms in such a form. So Rx is proportional to the, actually the voltage, measured voltage is just proportional to Rx. The coefficient is the energy, the electromotive force divided by 0. So for the reasonable Rx, A in R0, for reasonable A on R0, we actually got that the voltage is just proportional to Rx. Usually, such a measurement circuit is used when the Rx is small. In practice, up to 100 ohms somewhere, or maybe up to 1 kilo ohms, but usually in the range of 100 ohm and lower. If the voltage is higher, another circuit is in use usually. So now we use Rx as it's actually we use now additional resistor 2, but now we measure voltage not over the Rx, but over this resistor R0. And the equation, the voltage what will be measured is related to R0, Rx, and the electromotive force like this. So if the 0 is lower than Rx. So we will got this relationship between the voltage and Rx. So this is a reciprocal relationship. So actually we have a higher, so the higher is resistance, the lower is voltage. So it's a reciprocal relationship. So for the infinite resistance, we have a voltage in the round of 0. This type of measurement used for the higher resistances. So these resistances are high, not more than 1 kilo ohm. So such circuit is used. So that's why in a multimeters, so is it in a device used to measure resistance and voltage and current together, one device, so many in one. So if you look at the scale for the resistance measurement, you may find that this scale is reciprocal because such type of measurement scheme is used. So the voltage is reciprocal to resistance. So for the actually the 0 voltage correspond to the infinite resistance, and maximal voltage corresponds to the 0 resistance. Some of the multimeters which has additional scale for the low resistances, which is a proportional, not reciprocal. So, and if you look at such kind of devices, we still could find on the market. You see from the design, it's an entirely modern device. You can see the symbol of the magnetoelectric mechanical device. You could find numbers that provide you an the accuracy classes from the AC measurement, from the DC measurement, and from resistance measurement. So some other parameter may be written down. So you could see that here is a number of scales. It is a scale from a DC measurement, scale from AC measurement, which is a little bit shifted. It's some special scale for the resistance measurement and other type of scales. And by generally, this device is nothing more than electromechanical magnetoelectric meter with a number of shunts and additional resistances, which is attached to the device independent of the position of the switch here. We have the position of the switch here. And the circuit of such a multimeter looks quite complicated, but generally it's indeed it's broad, it is complicated, but if you take some time to try to dig into, so what we see here, we see a magnetoelectric device, a meter itself, and we see different shunt resistors or additional resistance, sorry, and different shunts, and one more additional resistors and additional resistors here for the voltage measurement, and a battery which is actually included to provide the measurement of the voltage and so on. And these long lines actually indicates that this type of rotatory switch, which actually when you switch it, it's put into connection. You may imagine that when you turn your switch, you have draw here vertical bar which shortcut in vertical direction, shortcut these contact lines. So if the bar is here, the contact is here. Yeah, and here we may see the way of the current. So from this way, here, that way, and where it should to here somewhere. Yeah. Well, if it's here, so it connects this and this point. So generally, it's just a set of shunts and additional resistors attached to. You could find here in the circuit some number of diodes. Could you imagine why do we need diodes here? Why do we need the diodes in this circuit? Any comment? Why do we need diodes? Is anybody here still? Just don't hear anyone. So please, your opinion. So let's remember that the meter is a DC meter. We couldn't work with AC. So we need actually the diodes to rectify our voltages and our currents and convert the AC into DC, if we may do this. And here is actually next topic what we discuss now. It's how to convert an AC into DC. And usually for such kind of simple meters, we use rectifiers, just a rectification. And as an example of the rectifier, we have here, we add just two diodes and provide the current flow through the ammeters only in one direction. So please note that we have to have the opposite way for the current in a parallel to our ammeter. So what could be the reason? Why do we need this second way? Yes, so if you look, so we have a one way to current with the diodes to the ammeter, and then we have the second way here. They are two, one way and second another. Why should we necessarily include the second way? No, it's not a feedback. It's to allow current to flow back. So when we have an AC current, it's flow one way, then it change in direction, flow another way. If we exclude this branch, we will got that the current couldn't flow back because of diode here. So we have to have a second diode. And for this, we have flow one way and another way. Yeah, so we need to add such. We need to remember that we have to provide for the current in both directions. Well, if we take such a simple example of the rectifier, in this way, the current that flow, if we have the AC current like here a blue line, so when we add the rectifier, we have the currents ammeter like this. So such type of rectifier is named as a half wave rectifier. So we got only half of the full wave. So the half wave. For such a half wave rectifier, the deflection angle for the ammeter will be proportional to the average current, that flow through the ammeter, and it may be related to the so-called effective current. Do you remember what does it mean, effective current, for AC measurement? What does it mean, effective current, effective voltage? Yes, exactly. For the sinusoidal, it will be divided by square root, as the amplitude value divided by square root of 2, but it's defined as the current that has, so the effective current value is the DC current value that have a same thermal effect as the AC current. So, and most of the such type of simple devices measure actually effective current. For the AC, sinusoidal current is fine. So there is some difficulties in measuring AC current. Why? Because In fact, if we look at the rectifier, and if we look at what will be the dependence between the angle, actually deflection angle, and the current, we will see that the deflection angle, in fact, is proportional to the average current. It may be recalibrated, so you may recalibrate by adding some, by alternating the sensitivity or adding some shunts, yeah, or adding some additional resistance. May recalibrate the system and make the angle proportional to the effective current. But what is the problem? That the ratio between effective current and average current depend on the shape of the signal. For the sinusoidal signal, usually the ratio between effective and average is approximately 1.1. For the triangle current or for rectangular pulses, the ratio will be different. So actually such type of devices usually are calibrated for the effective current, and they indeed show an effective current, but only if you have an AC, usual actually AC current of 50 hertz and so on. It doesn't work correctly, it doesn't show you correct effective current if you have a other shape of the AC signal. So for the other type of current, it shows a little bit different values. But generally, it's actually thought, usually such kind of devices, they are thought to an AC current from the net, so 60, 50 hertz and sinusoidal. There is another example, actually, this relationship could be a little bit improved. So if we take a half-wave rectifier, so we have a 2 here. Oh, sorry, no, we always have a 2 here. If actually these equations are enforced if we have a full-wave rectification. For the half-wave rectification, we have divide these coefficients one more. So the average is yeah, no, something wrong. Okay, with the 2 is for the half wave. We may increase it, the coefficient twice if we use the full wave rectifier. For the full wave rectifier, there is a different circuits. One of the circuits we use for resistor, for diode bridge, and here we get the current that flow through the ammeter will be such kind of pulsating current. But for the measurement device, we may use a little bit simplified circuit like this. So for this, we still have a full wave rectification, but it's not. I wouldn't say it's a simplest. It's not a simpler, but it's require only 2 diodes. And by the way, so here, if you look how the current is flowing through the amp here, we see that the current actually splits in 2 waves. So it flows through this resistor, it flows through ammeter and this resistor together. So in some extent, we may use this as a additional shunt like that. In fact, the current actually will split in 2. Nevertheless, so we will get a full wave rectification here. So for the measurement device, often such kind of circuit is used. Another aspect what should be taken into account, especially for high accuracy devices, so we need to compensate rectifiers for temperature and frequency, because the diodes behave very poor in high frequency. So when the frequency is high, the diodes start to pass current in a reciprocal direction. So they start to operate as a capacitors, and part of the current could go in opposite direction. Due to this, the current that is flowing through the ammeter here decreases. To compensate it, a 2-wave may be used. For example, we may add here capacity in parallel, so when the diodes, when the current through the amp decreases, but due to the high frequency, the total resistance of the whole circuit here decreases, and then the total current through all this assembly increases. By this, we compensate the decrease in the current flowing through of average current flow through the ampermeter. Here, the inductivity. Here the inductivity works in a little bit another way. So when the frequency increases, so the part of the current that directed here through the inductivity decreases too. So the higher part goes through the bridge, and the current through the arm increases as frequency increase. So because the inductivity here just block a part of the current. So we already agree that part of the measured current bypass our bridge, but when the frequency increases, this part will be decreased, compensating the compensating the current drop here due to reciprocal current of the diodes. The same with the temperature. When the temperature increases, in this way, the reciprocal current of diodes increases too. So it should be compensated as well, and we compensate it by adding some resistor, which resistance increases the temp, and the same idea. So we actually it's increased. So it shouldn't be cuprum here. It should be some other. So here is cuprum. So the resistance increase. So the part of the current bypassing the diodes increasing, and we got the compensation of the current decrease due to temperature. And here it should be not a copper. It should be some let's say it should be some thermistor is a negative temperature coefficient. This mistake should be correct here. It's not a copper, not a copper. It should be some negative coefficient device. Some other method. Yep. This one. This. Actually, it's an alternating resistor, so we may a little bit change by regulating this it's actually a potentiometer. So resist with a moving contact, sliding contact in the middle. So we may regulate it just balancing what part of this resistance should be shunted. Capacitor. So it's just for regulation. Yep. Generally, we may have here too some regulation, some choke or some inductance with some regulation. It's just for regulation. Well, some another example of measurement of the AC current. One of the quite accurate methods, also used very often because it's more expensive than just putting a diode in the circuits, is a thermal root mean square measurement method, which actually provide us directly this effective provide us directly with an effective voltage, because the measurement mechanism is the following. We use the measured current. It's actually more suitable for the current measurement, but may be done for the voltage too, when we convert voltage into the current via calibrated resistor. So we actually provide a measured current, provide a heating of the heat element, and heating element in turn heats the thermocouple. And the thermocouple being heated provide an electromotive force which is measured. So this is actually one very accurate method to measure effective current, because in fact the voltage would appear here depend on how much the thermocouple is heated. It's in turn dependent what thermal effect provide our current. So of course I wouldn't write that the voltage here will be equal, let's say, to the current here, but actually it will be proportional to the effective value of the current. The next is a question of calibration. So to increase the sensitivity of such kind of thermoelectric transducer, of electrothermal transducer. Now sometimes these transducers are joined together in a series to get an increased sensitivity, because this thermocouple provide an extra voltage, so they are added together. Sometimes these thermocouples could be included into the bridge circuit, and this bridge circuit actually prevent this device from the reaction on the outer temperature. So if the outer temperature grows or changes, in these cases, we get the thermocouple reacts on the outer temperature as well. So, in fact, to measure accurately with the thermo method, we need to thermostabilize this transducer to keep it in a constant temperature. So we can compensate for the change in outer temperature by switching all the thermocouples here in a bridge. So then when the temperature grows up, so all the thermocouples produce the same voltage, and the bridge remains not, how to say, it remains balanced. So there is no current here. Yeah. Here the current, here is actually the output device. So here we measure voltage of the thermocouple. Here we measure the current into the bridge, in the bridge. So it's of course we may measure voltage here too, not necessary to measure current. So either current or voltage between 2 points. But if we have some extra current, so this current actually provides the heating. Provides the heating of the thermocouples, and they actually there will be reaction. Well, so this is another example how to transfer, how to convert the measurement. But by the way, okay. Yeah. So speaking about the yeah, fine. We consider now some simple transducers and simple ways to transduce AC into DC. So we may make a break now, but I suggest to take a full-time break, but take it up to 2:15, and I'm going to end today a little bit earlier too. Yep. So let's take a break. Let's take break till 2:15.